Hey everyone, Wags here from Eagle Dynamics, and welcome to this first familiarization video for our upcoming DCS A-18C Hornet. This is our study level simulation of the A-18C Lot 20 as flown by the US Navy, although we will include other skins for operators of the A-18C, like the US Marine Corps, Finland, Switzerland, and Kuwait. Now in some ways, this is our successor to DCS A-10C Warthog, but it will be in fact a much more complicated and deep product that will be a great homey feel for the DCS world. In the coming months, I plan to create a series of these familiarization videos, with this first one being more of an introduction to many of the physical systems. Now as we integrate new features and systems, I will use these videos to introduce them to you. Now I'm sure as many of you know, the Hornet is a true multi-role aircraft. The Hornet includes a wide array of sensors, air-to-air weapons, and air-to-surface weapons. We believe this combination, with carrier operations in particular, will provide a lot of varied and very interesting gameplay for DCS world. So after literally years of research and data gathering, we've been able to gather enough information to bring you a very late lot F-18C Hornet, such that we can include several systems not available to older model Hornets. So that being said, while it's been a long wait, we do sincerely feel that it definitely will be worth the wait. So first, let's talk about some of the basic stats of the Hornet. An empty Hornet weighs about 24,535 pounds and can carry up to 27,365 pounds of equipment, fuel, stores, with a maximum takeoff weight of 51,900 pounds. It is 15.3 feet high and 65 feet long, and it has a wingspan of 40.4 feet that is further reduced to 27.5 feet when the wings are folded. It has a maximum airspeed of Mach 1.8 and a cruise range of 1,089 nautical miles. It has a service ceiling of 50,000 feet and has a thrust-to-weight ratio of 1.13 at 50% fuel. Let's now talk about the external structure of the Hornet. So being primarily designed as a carrier-borne aircraft, the Hornet was designed to withstand extreme environmental conditions with corrosion, strength retention, and durability in mind. The Hornet uses high-strength aluminum alloys as its primary structural material, and titanium is used in selected areas of high loading and fire containment. Steel is used in space-limited, highly loaded components such as the landing gear and the arrestor gear. And plastics are used in areas like the canopy, the radome, fairings, and edge members of the honeycomb doors. And then also carbon epoxy laminates are used in the vertical and horizontal tails and the wing main torque box skins, the trailing edge flaps, the access doors where its strengths can be used to its best advantage. And then their aluminum honeycomb structure, which is used in the leading edge flaps, the trailing edge flaps, avionic bay doors, the dorsal covers, the shrouds, the tailing edges of the ailerons, and the outer wing panels. So a redundant structure provides damage tolerance for both combat survivability, and the increased depth of the wing root efficiency really distributes the wing loads across the entire fuselage bulkheads. And further, the primary wing torque box and the multi-cell fuselage can carry maximum flight loads even after sustaining severe ballistic damage. And the wings themselves are actually attached with lug nuts to the fuselage, which actually simplifies the assembly and the maintenance of the Hornet. So the airframe itself is designed for 9 external store stations, several which are wired for 1760 smart munitions like JDAM, JSOW, and such. The leading edge extension, or the LEX, allows the Hornet to remain controllable even at high angles of attack. And the trapezoidal wing has a 20-degree sweepback on the leading edge and straight tailing edge. The wing has a full-span leading edge flap, and the trailing edge has single slotted flaps and ailerons over the entire span. The canted vertical stabilizers also enable the Hornet's excellent high angle of attack ability, including the oversized horizontal stabilators, the oversized trailing edge flaps that operate as flaperons, large full-length leading edge flaps, and flight control computer programming that multiplies the movement of each control surface at low speeds and moves the vertical stabilizers inboard instead of simply left and right. I'll now talk a little bit about the engines of the Hornet. Our Hornet is powered by two GE F404 GE402 enhanced performance engines, or EPE engines, that have over 4 million flight hours. In military power, each engine can produce 11,000 pounds of thrust. In afterburner, it's 17,000 pounds of thrust. These incorporate the same aerodynamic design of the earlier F-404G 400 engines, but use improved technology to provide up to a 20% increased thrust and improve reliability and durability by using advanced materials and high temperature and pressures. The air induction system has a simple ramp external compression inlets, and closely spaced nozzles and carefully contoured airframe nozzle interface minimizes aft end drag. The engines are interchangeable and crews can change them out quickly. Now, in addition to the engines, we also have two secondary power sources, the AMADs as well as the APU. Secondary power to the generators, hydraulic pumps, and fuel pumps comes from two airframe-mounted accessory drives, or AMADs. An auxiliary power unit, or APU, provides air to the turbine starter on each AMAD for self-contained engine starts. The APU can drive either AMAD when the main engines are decoupled, providing hydraulic and electrical power for system maintenance without the need for external power. As for the electrical system, the two AMADs drive two variable speed constant frequency generators. Two transformer rectifiers in turn provide the DC power. The Hornet is still mission capable with the loss of one electrical generator due to built-in redundancy. Two batteries provide DC power to operate the canopy and the APU igniters when still on the ground. The hydraulic system is actually two independent systems, each powered by a 3,000 psi pump. System 1 uses the left AMAD and only powers the flight control systems. System 2 is driven by the right AMAD and powers both the flight control system and the utility functions. Each system has two independent and isolated branches. Flight control and utility functions are in all four branches to provide redundancy and survivability. The fuel system consists of four fuselage bladder tanks and two integral wing tanks to hold 11,229 pounds of internal jet fuel. Two separate self-sealing feed tanks provide a protected get-me-home fuel supply. Each of these tanks supplies one of the engines through an independent feed system. An onboard computer monitors all fuel system functions and eliminates the need for ground support equipment. The flight control system of the Hornet uses a quadruplex control-by-wire flight control system, or FCS, with a direct electrical backup to all the control surfaces and a mechanical backup for both pitch and roll, which provides excellent handling qualities. It consists of two identical two-channel FCS computers that control the hydraulic-powered ailerons, dual rudders, horizontal stabilators, and the wing flaps. The computational portions of the FCS are quadruple redundant, while the hydraulic portions are dual redundant. The leading and trailing edge flaps are automatically scheduled for improved cruise and maneuverability throughout the subsonic and transonic flight envelope. A load factor limiter, or a G limiter, permits the Hornet to maneuver at its design limits without fear of overstress. This provides the pilot full use of the control stick without overstressing the aircraft and achieving maximum maneuverability in high angles of attack and roll maneuvers. Let's talk now a little bit about the payload of the Hornet. So one of the big reasons we chose to do the Hornet was its vast array of different ordnance that it can employ. We plan to include all weapons carried by US-operated F-A-18Cs. This includes the AIM-9 series, including the AIM-9X, the AIM-7 series, and the AIM-120 series for air-to-air combat. For air-to-surface, we plan all guided and unguided weapons and several training versions. Forward of the cockpit is the internal 20mm M61 M2 gun with 578 rounds of ammunition. As a Lot 20 F-A-18C will also include very modern weapons like JDAM, JCEL, and WICMIDs. So as development progresses during early access phase of the product, more and more weapons will be added. Now in regards to the sensors, there are four primary sensors that we'll be modeling. Now these include the AN/APG-73 multi-mode radar, the AN/ASQ-228 AT flare targeting pod, the AN/ALR-67 radar warning receiver, and of course the Joint Helmet-Mounted Cueing System, or JHICMS. In later episodes, we'll be returning to these for very detailed looks. So this concludes this introduction to our DCS F-18C Hornet, and a little look at some of the primary physical systems of the Hornet. In the next episode, we'll do a cockpit tour. I'll see you then.